Hello everyone, my name is Shreyas and along with my teammate Rohit, we have implemented this user level threading library in xv6. So here I have created a separate folder for this. We have three subfolders in this user threading library core folder, in which the first one is src, which consists of the main implementation of our project. Then we have test folder, which consists of the mutex test, and we have example folder, which consists of all the examples of the part that we have implemented after part 3. So let's move on to the main part. First, we have three main files over here. First one is uthreads.h, second is uthreads.c, and third one is uthreads_switch.s, which is used for context switching. So let's see the uthreads.h file. This consists of the main interface of our threading library. It consists of a thread structure, which consists of tid, which is thread id, state, then a stack for the thread, a save stack pointer, then the function pointer, which is used for the function to execute. Then we have the argument to start the routine, then we have the return value from this thread, and we have the thread id of the thread that is waiting to join this thread. The next part is that we have these thread states. There are 5 different thread states that we are going to use. We have the maximum 16 number of threads that we are going to allow. Then we have a stack size of 8 KB for each thread. Next we have mutex structure over here, which consists of a lock flag, which is going to tell us whether the mutex is locked or unlocked. Next we have semaphore structure over here. We have condition variable structure over here. We have channel structure, and apart from that we have foundation API functions, which are going to be implemented in .c file. These are all the functions that are going to present in our threading library. So this is the .c file, which consists of all the implementation of all the functions that are present in .h file. So let's start with the thread init function. This is the thread init function, which will initialize all the thread stalls to unused initially through this for loop. Then next is it will set up the main thread by assigning the thread id to 0 and its state as running. Then next we have thread create function. It will find the unused slot from the thread table and assign that to this thread pointer, and it will allocate a thread id to it. It will update its states and all other required variables. Then it will set up a stack for it. The logic for it's written over here. Then it will return the thread id of that newly created thread. Next we have thread join function. It consists of all the logic that is used to join the thread to this thread. The next part is thread exit function. It will update the state of the thread. Then it will, here the logic is written for the thread that is waiting to join this thread. Then we will call the thread schedule function, which will schedule another thread, and it will never return from here, so we'll just execute exit function over here. Next is thread self function. Then we have thread yield function. Then we have thread schedule function, but before that let's see the context switching implementation that we have implemented using assembly language. So here we will save the current registers over here through this logic. Then we will get the arguments from this stack. Then we will move the old register into this register, then new register into this register. Then we'll save the old stack pointer and this X register. Then we will load the next stack pointer, and this is the main function that will completely context switch to a new stack, and now we'll start running on the new stack. Then it will store the register from the new stack. Next let's see the scheduling algorithm. So here this thread schedule functions will perform this scheduling algorithm. It will find the next enabled thread from the queue. It will update its thread state, and if no runnable thread is found in the queue, it will simply return and keep the state of the current thread as running. If new thread is found in the queue, then it will update the current thread state as runnable and new thread state as running. Then it will perform the context switching. Next we have is synchronization primitive, which consists of mutex. This function will initialize the mutex. Then we have mutex lock function. It will try to acquire the lock, and if the lock is already held, then it will insert that thread into a wait queue. If the wait queue is full, then it will simply yield the CPU and change the state of the thread. Then when the mutex is unlocked, it will lock that mutex, it will acquire that mutex and update the owner id over here. Next is mutex unlock function. Then first we'll check whether we own the lock. Then next is we'll release the lock by these two lines. Then we will wake up one waiting thread from the queue. We will change its state. And next step is semaphores. Semaphores is I would say advanced part of mutex. It just has the counters for it. We have same wait function over here. We'll decrement the semaphore count over here. We'll if the count is less than 0, we need to block that thread and add it to the queue and change its state. Next is sempost function. Here we will update the counter of the semaphore. If the counter is less than 0, then we'll wake up the one waiting thread that is present in the queue and change its state as runnable. Next is condition variable function. In this we'll first initialize the condition variables. Then next is condition wait function. Here we'll add that thread to the wait queue. We'll unlock the mutex. Then we'll block the thread. Then we'll call the thread schedule function to schedule the next thread. Then when we wake up again, we'll log the mutex. Sorry, we reacquire the mutex. Next is condition signal function. We'll wake up the one waiting thread from the queue that is present. Then we'll find and change its states and we'll break. Next is condition broadcast function. This is used to wake up all the waiting threads that are present in the queue. Then we have channel implementation over here. In this we have channel create function, which is used to create the channel. Then we have channel structure over here. We'll allocate buffer to that channel. We'll initialize the fields present in the channel structure. We'll initialize the synchronization primitives that we are going to use in the channel. Then here is the channel send function. If it will check if the channel is closed. If it is closed, we will unlock the mutex. Then next is we'll wait until the channel is full. If the channel is closed somewhere in between while we are waiting, we'll simply unlock the mutex. Then next is we'll add the data to the buffer. Then we'll signal that data is available to consume, and then we'll unlock the mutex. Next function is channel receive function. In this we'll first lock the mutex. Then we'll wait until the channel is empty. If the channel is closed or it is empty, we'll return an error. Then we'll perform a condition wait operation over here. We'll retrieve the data from the buffer, and then we'll signal that the space is now available to add more data. Then we'll unlock the mutex. Next is channel close function, which is used to close the channel. We'll lock the mutex. We'll mark the channel as closed. Then we'll broadcast this message that the channel is closed now, and we'll unlock the mutex. Then channel destroy is used to destroy the buffer that is used for communication. So that's it from my side. Now Rohit will explain you the test cases.
I'm Rohit, and let's look at some tests. So first of all, we have Mutex Test. So let me just run it. Mutex Test. Yeah. So the context of test is basically we have 3 threads, and we have a shared variable, and each of the thread is making 10,000 increments to the shared variable. And in the first test, which we are doing with the without the mutex protection, the final value of the shared variable is 10,000. So we have lost the 20,000 increments. And in the test 2, which is with the mutex protection, the final value of the shared variable is 30,000, which is expected, and which demonstrates that all of the threads are able to make their 10,000 increments each, and no operation is lost. Next one, we have a producer consumer test with semaphores. Here we have 3 producers. They are each producing 10 items, and we have two consumers, and we have a buffer size of 5. So here the 3 producers make 10 items each, and 2 consumers process them in buffer size of 5. The empty semaphore the prevents the overflow and it fully prevents the underflow, and mutex protection protects the buffer access. You can see producers and consumers interleaving, and at the end all 30 items are produced and consumed correctly. So after that we have producer consumers with channel states. So let me just run that. Okay, so similar to before, we have 3 producers producing 10 items each, and we have 2 consumers, and channel capacity is of 5. Again you can see the producers and consumers interleaving. This implementation is much cleaner. There are no explicit semaphore. The monitor closes the channel when producer finishes. Consumer gets -1 from the closed empty channels, and it exits gracefully. And in the end you can see all the 30 items are produced and consumed correctly. Yeah. After that we have reader writer with writer priority lock test. So just run that. Okay. Here we have 3 readers and 2 writers, and the writers have a priority, and they get the exclusive access to the shared resource, and it blocks the reader when it is writing. You can see the multiple readers reading simultaneously with the same value, but when a writer wants access, it blocks the new reader. It gets exclusive access, updates the value, and when writer finishes first, because it has priority, and after then only readers will produce. And you can see the final value of 6 matches the expected value. So that's about the test.
Quickly go through the part 4 of our implementation. It consists of 2 files, which is asyncio.h and asyncio.c file. The asyncio.h file consists of a structure which tracks each IO operation. It stores the file descriptor, buffer, and whether it's completed and which thread is waiting. Then we have this async IO read function. When a thread calls this function, it submits a request to the global queue and returns immediately without blocking. Then thread calls this the IO wait function, which sets its threads to sleeping and yields to the scheduler, allowing other threads to run. Now we'll quickly move to the .c file and see the implementation. Here we have implemented a worker function which continuously scans for pending requests. When it finds one, it performs the actual blocking, which is the read system call, and marks the request as complete and wakes the waiting thread by setting its state back to runnable. And not in this blocking actually happens in the worker thread and not in the application thread. Now I'll quickly go through the demo of this test case here. Yeah, so this is the output of our code. Here you can notice that there are 2 different process IDs for producer and consumer. So this proves that there are 2 separate processes, and basically this garbage output is due to that 2 processes are trying to write on the console at the same time. And you can see that the items being produced with their byte counts and consumed by the threads. Here's the critical result. There are total 20 items consumed, and all items were successfully transferred through the pipe with no race condition or lost data. The consumer thread consumer thread 0 consumed all 20 items, and consumer thread 1 consumed 0 items. So I think I would say that this is not a bug. It demonstrates the realistic thread competition, where one thread was simply faster at grabbing the items from the pipe. So that's it from my side. Thank you so much.